I can't just be blabbing all day, right? Okay, so let's do this thing. Oh, I have a note here, caught my eye. Good thing too. If now there's only 2 of you here, but if you have some time to do my evaluation, so every now and then you get, or as a teacher, you get picked to do evaluations. You might have done them for other profs already, but I'll show you how to get there. Oh, I was looking up. I decided to go another way. You'll see on Friday. Moodle. So I've been chosen to be evaluated by you guys. And so on your Moodle page, you should have in progress, and it might be on like the next page, it is for me. You should have, there it is, formative evaluation of college professor course, I guess. And there's all these instructions, blah, blah, blah. They're claiming it's going to take 25 minutes. I don't really think so, but maybe. And then if you go to the survey link, well, read the instructions first, but and then you hit next, and then you choose me. You would think that it would know who your profs were and then just narrow it down, but whatever. And then you select your course. And then in case you're tight on time, the part that's important is these, the actual survey questions, the strongly agree to strongly disagree ones. So if you scroll through, it looks like a lot. It's not really a lot, but those answers go to the dean, who's my boss. And so those are the important numbers. And then there's comments, which I enjoy reading, but those only go to me. So if you're short on time, you can skip the comments. Don't worry about it, unless you know you have something you really want me to know about. But then it probably won't take that long. I used to just agonize over the things to write in here. Oh, I need to like write something really good. And then I realized it just goes to the prof when I was teaching. So so those ones, don't worry about those ones. Just the actual survey questions are the important part. But and then of course I appreciate feedback if you have time to give it. And that is due on Friday. I didn't actually catch what time, but it's in the instructions there. So if you could do my evaluation, this is more for the people who are not here today. If you could do my evaluation, I'll just say due Friday, I would appreciate it. So let's see here. Oh, I was also, Carly, I was chatting with David about whether you guys want to have a quiz 8, which would be basically on this week's stuff. I would put it off until Friday and postpone it a little bit. But then it gets a little bit overwhelming is what I worry about, because you've got a test on Wednesday, test 3 on Wednesday. So I don't want to overwhelm you guys with like quizzes and tests and finals and oh my. So we can just kind of think about that. If you want to have a quiz 8, I can, yeah, a shorter one. Another thing I was thinking about was maybe if I make it like a bonus quiz. So then if you do it, you can boost your quiz grade. And if you don't want to do it or don't have time.
Yeah, that works.
Yeah, cool. Okay, done. Let's do that. So quiz 8. will be a bonus quiz. Okay. And it'll cover covering 4.2, 4.3, 4.4, and 4.7. Okay. And you can use it to kind of practice before the test, and it'll be available after class, because I don't want you to feel hounded by it now, because today we're going to do 4.2 and 4.3 with a little bit of luck, and then on Friday we'll do 4.4 and 4.7. So it'll be available after class on Friday until Tuesday, April 13th at 11:59. Okay. So let's use it as a bonus quiz. And if you get a chance to do it, great. If you don't worry about it. Okay, and I'll try to make it short, or as short as I can. Okay. So let's see here. It's been so long since we met. We are going to sort of review. So last day, what did we do last day? Oh, maximum and minimum values. We're actually going to keep talking about maximum and minimum values today. And so I'm not going to review it. We'll review it as it comes up. So section 4.2 is called the mean value theorem. The mean value theorem. If you haven't taken any statistics, then you might not know that the mean is the average, right? So the mean is the average. Okay. And so it's going to be kind of weird and link us back to the beginning of derivatives, essentially. But before we go down that path, we have to introduce Rolle's theorem. And Rolle's theorem is on the handout, of course. And what I find with a lot of these theorems is that if I take a step back, then most of them are pretty obvious. Not necessarily, but some of these things will feel obvious, and that's okay. We need them just to kind of to prove stuff and to prove that functions behave the way that we think they do. So Rolle's theorem says that if we let f be a function that satisfies the following three hypotheses, then, so first things first, f is continuous on a closed interval a to b, and we looked at that last day, right? We have to have a continuous function, and it has to be differentiable on this open interval. And I do want to talk about kind of what that means, just a refresher. But before we do that, we also need f of a to equal f of b. Notice that a and b are the endpoints. And so what that means is that you start and end in the same position. So, you might have some activity going on, but your endpoints are actually the same. Then what Rolle's theorem says is that then there's a number in AB where the derivative is equal to 0, right? So where we have this kind of plateau, or maybe a maximum or minimum, right? And so let's talk a little bit more about point number 2 specifically. What does it mean to be f is differentiable I put like this huge grip on my pen so that because my hand has been just giving me grief, but now I can't write for my life. So anyways, I guess it's good. So if f is differentiable, that means that we can't have any corners, right? We can't have any vertical tangents, right? And so this means that there are no places in the interval where the derivative at this point does not exist, right? Things like, right here, f prime of c does not exist, and maybe something like right, so no corners or cusps or anything like that. And then the second part is that, okay, well, it has to be differentiable on an open interval, which means we're just allowing for, so on an open interval, allows for non-differentiable endpoints. So it could just end there, the function, it doesn't necessarily keep going. So allowing for non-differentiable endpoints. So there are a couple of examples where it is satisfied. Let me bump this to the top here. So it had to be continuous. All of these look continuous to me, right? It had to be differentiable, so there are no cusps, there are no vertical tangent lines, so it looks good. And it looks like all the start and the end points are all the same, which was part of Rolle's theorem. And what we're going to find here is that, okay, well, if all those things are satisfied, which they are in all those graphs, then there is some number in this interval where the derivative is 0. And notice there, here's 1, right? Here the derivative is always 0. Here there's actually 2 points where the derivative is 0. That's fine, right? It's just at least 1 point. And then here we have another point where the derivative is 0. So that's good. Notice here, right, can have 2 points, right? 2 or more points. You can have as many points as you want. But I think the theorem, the theorem only talks about 1, but it allows for as many as you need. Okay. Let's see here. Whereas if we have this kind of graph where maybe they were supposed to end at the same point. Pretend it's the same point. Right here, the derivative at x1 does not exist, and the derivative at x2 does not exist, if we call this x1 and x2, right? So it's not differentiable, right, on this open interval, and so Rolle's theorem does not apply. Not differentiable at all values in the A to B. So Rolle's theorem does not apply. Okay. So we've already sort of seen this, right, with way back with the intermediate value theorem, where we said, okay, well, if I'm able to evaluate this function and I find a negative value and a negative output, and then I find a positive output, then what we went to was, well, at some point, this output must be 0. And it allows for, at least one time. So we're going to build on that today, and just kind of zero in on how many zeros we have, or how many solutions to f of x equals 0 are we going to have. So to build up to that, let's consider a quadratic. A good old quadratic. F of x equals ax squared plus bx plus c. This is a polynomial, and we know that polynomials are continuous and differentiable, and so we're gonna, be working with a lot of polynomials because they definitely satisfy that criteria. So let's just highlight that, right? A polynomial, therefore continuous. And that's just for all polynomials, continuous and differentiable. Oops. And differentiable on the set of real numbers, meaning from negative infinity to positive infinity. Doesn't matter what value of x, they all go, they all work. So what we know about the quadratic, right? We can think about the shape of a quadratic. It's going to be this parabola, right? Either facing up or facing down. So logically, we could have no solutions to f of x equals 0. We could have one solution, right? Graphically, the quadratic, it could look like, I don't know, something like this, right? Where we have two solutions. And by solutions, I mean to f of x equals 0, where does this thing cross the x-axis? Those are typically called solutions. And so, or I could have, maybe I've got something like this, right? Where this thing will never cross the x-axis, right? And so here we have no solutions. Or the kind of special case of one solution would mean that it just touches the x-axis there, right? And then that's what one solution would look like. So it helps knowing the shape of this graph. That's not always the case, right? But it helps for establishing the idea, because we know the quadratic, what it looks like. So, okay, so we have kind of three options, right? And if we tried to claim that there are three solutions, well, that makes no sense. So that'll never happen. So a question we might ask is, how many solutions are there are there to f of x equals just a general quadratic ax squared plus bx plus c equal to 0. So what we're going to do is we're going to say, okay, we know it's impossible, just looking at the graph, we know it's impossible to have 3 or more solutions. So what we're going to do is we're going to approach this by contradiction and say, how about we pretend we have 3 solutions, and then we're going to find that things fall apart. And that's a proof by contradiction, and it's actually really common that we use that as a proof, because sometimes it's easier to prove that something doesn't work, and here's the proof, than to consider all the options where it would work. So how many solutions are there to this thing? We know it's impossible. We know it's impossible for ax squared plus bx plus c to equal 0 at 3 values. Right? So we consider a proof by contradiction. Oh, should say contradiction. So we say if there are 3 solutions, right? We know there aren't, but if there are 3 solutions to f of x equals 0, just in general, f of x here is a quadratic, then there should be 2 horizontal tangent lines, right? If you have 3 solutions, and I'll map it out here, then there should be 2 horizontal tangent lines. And if we think about, I'm forcing 3 solutions here. I'll space them out evenly. Oops. Maybe it goes like, I don't know, like this. Something like that. Right, so then we say, okay, well, at some point, right, we would need 2 horizontal tangent lines. Okay. Which means that f prime of x equals 0 at 2 values of x. We can take the derivative of a quadratic. In fact, at this point in the course, it's really fun to take the derivative of a quadratic, right? F prime of x is going to be 2ax plus b. And then now I'm going to shift that over and set it equal to 0, right? 2ax plus b equals 0. So I get 2ax equals negative b. Remembering that a and b are just constants, and c, but the derivative of a constant is 0, so that's why it's gone away. So x is going to be negative b over 2a. This is only one value. A and b are constants, and so this is only one value where the derivative is 0. So there's only one horizontal tangent line. Right. Therefore, f of x equals ax squared plus bx plus c equals 0 can have at most 2 solutions, right? Because we assume that, okay, let's pretend that we have 3. How would we do that? And then we find that we can have at most 2 solutions. So f of x equals 0 can have at most 2 solutions.
I think I might have blanked out a little bit. And how did we get from, okay, we've got one horizontal tangent line to at most 2 solutions?
Because if you have one horizontal tangent line, right, that looks like this, or like this, right? And if there's only ever one point, then if you cross the x-axis here or here, right, then you would have 2 solutions. But another option would be you would still only have one horizontal tangent line, even if it looked like this, right? And you would have a horizontal tangent line here as well, but with no solutions. And so you could have 2 solutions, no solutions, or 1 solution, but that's why it says at most, and that's important.
So if the function had been, or had potential to give like 2 horizontal asymptotes, it would have output 2 values as opposed to just the 1.
Yep. So what would happen here is one way to get multiple values of x is if you have x squared here, because then when you take the square root, you'd have the positive and the negative version of it, right? So so then you would be able to show that you have multiple horizontal tangent lines.
Okay, that makes a bit more sense.
Cool, nice, good. So kind of in a similar way, we're going to apply Rolle's theorem with the intermediate value theorem. So kind of we're going to get like a flow going here. So we can apply Rolle's theorem to other functions in the same way. So we'll start with, and maybe I'll bump this down because it's kind of a new topic here. So we'll start with some given f of x, right? Open to any function f of x. From the intermediate value theorem, we can use the intermediate value theorem to kind of zero in on, pun intended, I guess. If we are able to evaluate f of x and find a negative output or a positive output, and then evaluate f of x at some other random point, and you find the opposite sign, then somewhere in there you have at least one solution, right? So we kind of narrow down using the intermediate value theorem. Is there even a solution to find here? And then we use Rolle's theorem to prove that there's exactly one solution, right? So let's see here. So you start with an f of x, and then oops. Let's kind of do them listwise. So you're given some function, and then you use the intermediate value theorem to show that f of x equals 0 has at least one solution. So then we use, then you're going to show that f of x equals 0 having two or more solutions is impossible using Rolle's theorem. And then your conclusion, f of x has exactly one solution, or f of x equals 0 has exactly one solution. And that's what I'll get you to do on the test and on the final, is just I'll give you a function, and then so first you have to use the intermediate value theorem to show that it has at least one solution, and then you can go ahead and use Rolle's theorem, which I'll do an example, to show that it can only have one solution. So let's grab an example here. Oops. Prove that this equation, which is a polynomial, right? So that's good. We're off to a good start. Has exactly one real root. This is a solution, right? Roots are solutions, so where f of x equals 0. Just to get it out of the way, right? This is a polynomial. Therefore, it's continuous and differentiable on the set of real numbers. All right, so that's good. Polynomial. It doesn't really look like polynomial, does it? Close enough. Okay. So we've got a polynomial, so that's good. We're kind of off to the races there. And then what we're going to do is we're going to start with the intermediate value theorem to see if maybe, because we're not given an interval, maybe we're able to find an interval where we get a negative and then a positive output, or the opposite direction, right, where it crosses the x-axis. So first things first, is f of x continuous? We already established that. Yes, right. But that's a key thing to having this intermediate value theorem, right? Because if it's continuous, then you know that, okay, if you are able to find 2 points, then it's going to be continuous between. So pick arbitrary values to test. Maybe let a be 0 and b would be 1. If those don't work out, then go ahead and choose some different numbers, kind of play around with it. But often kind of 0 to 1 is a good choice, 0 to 2. You could even go, into the negatives, -1 to 1, something like that, right? But just kind of picking values here. So f of 0, just evaluating the function at 0, is 0 to the power of 3 plus 0 minus 1 puts me at -1, which is less than 0, right? Negative. And if I try f of 1, I get 1 to the 3 plus 1 minus 1, which puts me at positive 1, which of course is positive greater than 0, right? By the intermediate value theorem, I'm kind of paraphrasing my notes here, there exists some value, right, between 0 and 1, because at some point it must have crossed the x-axis, right, and been 0. So by the intermediate value theorem, there exists at least one value C in 0 to 1, where f of c equals 0. Okay, so here, right, we're able to say, okay, well, somewhere in this function, we were able to zero in on at least one solution, okay? So, and we just picked an interval, right? We don't really need to be limited to this interval, but we need some interval for the intermediate value theorem. So then we move on to Rolle's theorem. Where we're going to show that f of x equals 0 cannot have more than one solution. So again, right, because the question was show that this thing has exactly one real root, so one solution. And that's what I'm going to get you to do too, right? So, so again, we kind of approach it by contradiction and we say, okay, well, let's pretend that we have two solutions. So if f of x equals 0 has two solutions, let's say x equals c1 and x equals c2, just for simplicity, then the derivative at x equals 0 at some point, right, between these two values, c1 and c2, because these are where it crosses the x-axis, right? So at some point between those 2 points, you must have a horizontal tangent line somewhere, right? It had to change course. So then the derivative is 0 at some point between c1 and c2. Since f is differentiable, right? There's no point where things fall out. Differentiable over the set of real numbers. Okay. So what that might look like is here you are at C1 and C2. Well, to get from C1 to C2, you might have to have something like this, right? Which means that at some point, you're going to have a horizontal tangent line. So what we're going to do is we're going to take the derivative, of course, and we're going to force it to be equal to 0. So the derivative of f of x, let's remember, I can't remember what the function was, x to the 3 plus x minus 1. Maybe I should jot that down, x to the 3. This is more for me, x to the 3, let's see if I have it here, plus x minus 1. Just otherwise getting the derivative out of nowhere here. So the derivative of that thing is just 3x squared plus 1. So now I'm going to force it to be 0 3x squared plus 1 equals 0. Often I'll kind of do this kind of daisy chain, right? So I'll find the derivative and then I'll force it to be equal to 0. Not on the same line because, I don't know, it just looks a little bit messy. So then I kind of bump it down, but you can do the same if you want. So now I can solve for x. So 3x squared is -1 and x squared is -1 over 3. Hold up. What does that mean? Well, it's telling us that some squared value, which we know is always positive, is going to become negative. And so what this tells us is that there's no solutions, right? And so here, no solutions, right? There is no value of x that you could put in there to get -1 over 3. Right? Also, if you tried to keep going, right, and take the square root of a negative number, we also can't do that. So kind of whichever way you want to approach it is fine, but there are no solutions. So what does that mean? It means that f of x, therefore, f of x has no horizontal slope. Right? F of x has no horizontal tangent line. I'll say that instead of slope. Tangent line. And because there's no horizontal tangent line, right, that means that it doesn't need to go back to the second solution because there is no solution, right? And so f of x has no horizontal tangent line, which means f of x equals 0 cannot have a second solution. Therefore, f of x equals x to the 3 plus x minus 1 equals 0 has exactly one solution. Good. So feels kind of wishy-washy, right? But just in general, right, you use the intermediate value theorem to prove that a solution exists. And if you can't do that, then there are no solutions and you don't need to worry about it, right? But if you're able to prove that there is a solution somewhere, and then you kind of narrow it down with Rolle's theorem and say, okay, well, because of the fact that if the two outputs are the same, so making them 0. So because there's no horizontal tangent line, there's only one solution. Because you can only get this kind of horizontal tangent line if at some point it goes from some value C1 back to C2. Yeah, so it's a little bit weird. You'll definitely want to do some practice problems kind of to see what they want. But yeah, good. But you can follow this procedure. It'll work. Okay. Now for the big guy in the show, the mean value theorem. Oops. The mean value theorem is kind of weird in my opinion. I know it's important. Likely because it simplifies a lot of situations. I don't know. I don't know a lot about when we would use the mean value theorem besides to kind of average out. And if if finding the derivative explicitly is difficult, then you can use the secant line instead, because at some point, so the mean value theorem says that at some point, the slope of the secant line connecting the two endpoints is going to be the same as the slope of the tangent line at some point in that interval. So the mean value theorem says that if we let f be a function that satisfies the following, so f has to be continuous on a closed interval, a, b. So we do need a closed interval. And then again, f is differentiable on an open interval. So again, it's allowing for these non-differentiable endpoints. These are the same conditions as Rolle's theorem, right? So, but Rolle's theorem added that the two endpoints have to be at the same point, and now we're moving away from that. So then there's a number c in this interval, so that the derivative at this point, right, is the same as the slope of the tangent line, right? Rise over run. You could also rewrite it this way just by multiplying, which way? Multiplying b minus a over to the left-hand side and kind of switching sides, right? So whichever way is easier to look at. I usually just go for this version. I find that it's easier, and then I just kind of morph it to here if that's easier to deal with. But I want to focus on this statement here. Come on. Right, what does this mean? Well, it means the slope of the tangent line at C is equal to the slope of the secant line, connecting the endpoints, A and B. Okay. So graphically, what does that look like? I put two examples here. Let's just grab them. I'll shrink them down. Oh, you know what? I think they were separate here. Okay. So here, the secant line, remember we used the secant line to approximate the tangent line. Now we have the derivative, so we don't need to do that anymore. But again, right, so here, the secant line is just a line that connects 2 points on a function or in a function. So here, the blue line is the secant line, and then what the mean value theorem says is that at some point in here, you will have a point where the slope of the tangent line is the same as the slope of the secant line. So let's have a look at that worked out example in here, because it's got kind of the gist of it. I'm not going to copy it in, but if we have x to the 3 minus x and the endpoints are 0 and 2, so again, we have a polynomial, so that's great because we know it's continuous, we know it's differentiable, and so we're off to the races here. So what the mean value theorem says is that there is some number c inside 0 to 2 where the derivative is the same as the slope of the secant line. And so we want to find that point where it is the same, so it has the same rate of change as the secant line. So we can plug in our values, right? If we have f of x and we want to talk about f of 2 and f of 0, right? We can evaluate those. And what we're going to find is that at some point c, the derivative is 0. So what we get here is we can evaluate the derivative and evaluate it at c, right? And substitute that in, and then we can solve for c, and then we have that point where the slope of the tangent line is parallel to the slope of the secant line. So a little bit weird, but it's definitely easier to just find the slope of the secant line from the endpoints, right? And then knowing that at some point in here, the slope of the tangent line is the same as that, then I guess that can be useful. So I say I guess because we definitely don't use it in statistics, and I don't know when you would need to use it. But anyways, that's my bad. I should know. Let's see here. I want to make sure that, okay. Before we do this example, I actually want to add another example that's not in the notes. Because it's a little bit more straightforward than what we are going to do eventually. So if we have, if f of x equals 2x squared minus 3x plus 1 on the interval 0 to 2, notice 0 to 2 is like the preferred interval, I think. Find the value of x where the tangent line is parallel to the secant line. So first things first, let's find the slope of the secant line. And so we know we can find the slope of the secant line f of b minus f of a over b minus a. Oops. Oopsies, which is f of 2 minus f of 0 over 2 minus 0. F of 2 is 2 times 2 squared is 8, minus 3 times 2 is 6 plus 1, minus f of 0 is 1. 0 minus 0 plus 1 is 1 over 2. 8 minus 6 is 2 plus 1 minus 1 is 2 over 2. So the slope of the secant line is just 1. So the overall rate of change from the beginning to the end is going to be 1, which means that at some point in this interval, there has to be a tangent line with a slope of 1 as well. So by the mean value theorem, the MVT, the derivative of f of x is equal to 1 at some point since f of x is continuous and differentiable. you're always safe to throw that in, especially if you see that you have a polynomial. You can just kind of tack it on. Oh, okay, and I checked that it's continuous and differentiable, so that's good. I wouldn't get you to work with functions that are not, but it is something that you have to check. So, okay, so we can find the derivative of the polynomial. That's fine. 2x squared makes 4x minus 3, right? If you take the derivative, and then I'm going to force that to be 1 and solve for the value of x. That makes that happen. So I get 4x equals 4, so x equals 1. Therefore, at x equals 1, the slope of the tangent line is the same as the slope of the secant line connecting the endpoints. Connecting the endpoints. So that's kind of the straightforward version of the mean value theorem. Just find the value where the slope of the secant line is the same as the slope of the tangent line. The example from the notes is a little bit more involved. So if I tell you that f of 0 is -3 and that the derivative of this thing is always less than or equal to 5 for all values of x, how large can f of 2 possibly be, right? So now we're kind of working a little bit backwards to try to pinpoint, okay, well, how large could, if we're talking about the interval from 0 to 2, basically it's asking how large could that endpoint possibly be, right? So we're told that, f of 0 is -3, and also that f prime of x is less than or equal to 5. Because the derivative, we're told that it's less than or equal to 5, that's implying that this thing is differentiable over all x and therefore continuous. So now we're kind of going backwards, but so therefore differentiable, which implies that it's continuous. Right, kind of working backwards. So by the mean value theorem, there exists some number c, there exists a number c such that we'll start with just the basic mean value theorem, which says that f prime at c is the same as f of b minus f of a over b minus a. Right? That is the mean value theorem, assuming that it's continuous and differentiable, which it is. So, okay, we're told that f of 0 is -3. So let's let that x equals 0 be our starting point. And then because we're concerned with f of 2, how about we let b be 2? So we're going to let a be 0 and b equal 2. So then what we find is that f prime at c is f of 2 minus f of 0 over 2 minus 0. Okay. So a couple of ways that we could take this, but what I'm going to do is I'm going to bring this 2 over to the left-hand side because I know something about the derivative. The derivative has to be less than or equal to 5 for all values of x. We also know that this is equal to -3. Right? So doing some substitutions and kind of mixing things up here, I'm going to find that I have 2 times the derivative at c is f of 2 plus 3. Right? So then if I kind of focus on f of 2 because that's the value that I'm interested in, right? Then I can have 2 times the derivative at c minus 3 is equal to f of 2. We know, just for f prime at c, we know f prime of x is less than or equal to 5 for all x. Right, so it definitely applies in the interval 0 to 2. So what does that mean? Well, it means that 2 times something that's less than or equal to 5 has to be less than or equal to 10, right? So let's kind of work that out here. 2 times the derivative of, let's talk about x in general, is less than or equal to 2 times 5. Right? Just multiplying both sides by 2. And basically, I'm just morphing it to look like this whole side here, right? So if you want to build it up, so you start here, okay? F prime of x is less than or equal to 5. Multiply both sides by 2. So then, and then next thing I could do is, well, I could simplify, right? 2 f prime of x must be less than or equal to 10. Or I could keep going and I can just subtract 3 from both sides to build it up to look like what I have here on the left-hand side. So then 2 times the derivative of x minus 3 is less than or equal to 2 times 5 minus 3. Which means that 2 times the derivative, and I'll change my x to c. You can bounce back and forth. You could have kept it as c all the way through. It's just that our original inequality was in terms of x, but you can bounce around for this one. It must be less than or equal to 7. But we also said that, okay, well, f of 2 equals this, so then f of 2 must be less than or equal to 7. And maybe I'll do a little subtract 3 from both sides. And then since f of 2 is equal to 2 times the derivative at c minus 3, which is less than or equal to 7, right? We know f of 2 must be less than or equal to 7. So the largest possible value of f of 2 then must be 7. Therefore, the largest possible value of f of 2 is 7. Oh, sorry, Carly. was on a roll. Let's go back. Yeah, I think it was this one you were asking about. 2 minus 0, I just simplified to 2 and then I brought it over in one musical move. It. Sorry about that, Carly. Okay. 4.3 is our next section. And we're not going to do a ton in there. And it's not really going to introduce any new skills. It's just new applications. So let's see here. Any questions about the mean value theorem though? I'm assuming you'll ask me and then I'll not read the chat for a few minutes. And then you'll sort it out yourselves. Yikes, sorry. So section 4.3, it's just developing some graphing skills. So we can use derivatives to figure out what the graph looks like. And I didn't ask, do you guys want a break? This would be the time to take a break, I guess.
The break I'd want would probably involve like a 15-20-minute nap that would morph into like an hour-long nap. You know how it is.
Okay, yeah, let's just do 4.3 then, and then yeah, call it a day. Okay, so we're going to talk about how the derivatives affect the shape of the graph. So we know the derivative is the slope of the tangent line. So of course it kind of tells us about the behavior. But now we're just going to kind of lay it out and spell it out, I guess. So how derivatives affect the shape of a graph. If you have a look at the handout that I posted, we're only going to do one example, but there's a lot of stuff here, right? So what I want to do first is I just want to talk about all these points, and then we're going to apply it with that example. So I'm not going to bring in all of these at the same time. I'll bring them in as we use them in the example. So kind of a little bit different, but let's just talk about all these things. All of things like where is it increasing, where is it decreasing? I know we cover in pre-calculus, so if I gave you a graph, you could tell me where it's increasing and decreasing, right? And you could also tell me if the slope of the tangent line is positive or negative, right? So, and the slope of the tangent line is the derivative, so all of this is kind of falling into place, right? So first thing we can talk about is increasing or decreasing in general. So if the derivative is positive, right, then we're increasing, the function is increasing on that interval. So, and what we've seen is that maybe we have, inflection, or not inflection points, maximums or minimums where we change direction, right? So, and then of course, if the derivative is negative, then we have a decreasing function on that interval. So this kind of takes us to the first derivative test. And if we scroll down, you'll see that there's a second derivative test, which if you kind of do a compare and contrast here, you'll see that they're both looking for local minimums and maximums. You only need one of these tests. So if you're going to focus on one of the tests, use the first derivative test because it'll always work. Uh-oh. Our time is numbered. 10%. Oh, because I was using my iPad before. Dang it. Anyways, hopefully we'll make it. So if you want to kind of clear your mind of some stuff from this section, just focus on the first derivative test and just parking lot the second derivative test. Okay, they do the same thing. Yeah, exactly. You know me so well, David. Okay, so we want to find our critical numbers first. And critical numbers, we talked about them last day. Critical numbers are either where the derivative is 0 or where the derivative does not exist. Okay, so if we have C is a critical number and we have a continuous function, so kind of specific here. If the derivative changes from positive to negative, well, then you have a maximum, right? If the derivative changes from negative to positive, then you have a minimum, right? So we can use these derivatives to figure out if we have a local maximum or minimum. If the derivative doesn't change, right? If it goes from negative to negative or positive to positive, then we have neither a local max or min, right? So something like this. This is a critical value, right? Because the derivative is 0, but going from one side to the other, we still have positive slopes all around. So there's no max or min there, right? So here are all the different options. But if you kind of map it with your hand, right, a positive slope is going up and then a negative slope is going down, you can figure out whether you have a max or min without kind of looking at the first derivative test. But that's what it's doing. If you have this kind of bowl shape, right, so it's kind of facing a bowl facing up, I guess, then we say that it's concave up or upward. And if it's kind of concave down, I don't know how else to say it, this kind of hill situation, right, where if you, does it talk about the, oh yeah, if you map your tangent, you could talk about it in terms of the tangent lines, right? Here, all the tangent lines would be on top, right? Not really helpful, in my opinion, to remember that that means that it's concave down. But just remember that if it's kind of cupped like this, then it's concave down, and if it's up, then it's concave up. We can find concavity using a concavity test, using the second derivative. So the second derivative, if the second derivative is positive, so remember the second derivative is the rate of change of the rate of change, right? So again, not something that I find helpful, but it's true. If the second derivative is positive, right, then we find that we have this concave up situation. So that's just something to keep in mind. If we find that the second derivative is negative on some interval, then we have concave down. Notice that we can change, right? Sometimes it changes at some inflection point where it goes from concave down to concave up. Okay. How do we find those inflection points? Well, an inflection point is where the curve changes from concave up to concave down, right? And so what we can do is we can figure out, okay, let's use the second derivative. Where is the second derivative equal to 0, right? Second derivative equal to 0 doesn't mean what the first derivative equal to 0 means, right? But that's where it's going to change from being positive to negative, or the other way around, right? And so we pick out those values where it's 0, and then those are our cutoff points, right? And so those will be our inflection points. Okay. Then we've got the second derivative test, which I will talk about, but again, it's not that powerful in comparison to the first derivative test, but it still works. Suppose that the second derivative is continuous near C. So now we're talking about the second derivative, but also if the first derivative is equal to 0, so this is a critical number, and we were calling it type 1, right, where the derivative is equal to 0 versus the derivative not existing. So if you have a critical number where the derivative is 0 and the second derivative is positive, then you have a local minimum, right? So if you're concave up and you're at a critical number, then you have a minimum, right? If you're concave down, right, so the second derivative is less than 0 and you're at a critical number, then you're at a maximum, right? So that's what it's saying, but it's got all these specific requests, right? The second derivative has to be continuous, but also we can only have these very specific critical numbers. It works sometimes, but the first derivative test, as long as we have a continuous function, will always work. So as promised, let's go through and do this example, and what I'll do is I'll bring in the blurbs as we use them. Just for some practice, I added increasing and decreasing as well to the list. But also, I think when I looked at the WebAssign problems, they get you to do increasing and decreasing, and so I figured we may as well do it. Okay. I've got a note here, but I'm going to introduce it at the end. It's just that blurb about the second derivative test not being very powerful. So if we have f of x equals x to the 4 minus 4x to the 3, we're happy because this is a polynomial. Polynomial, therefore continuous and differentiable on the set of real numbers. Right, so that's good. Get that out of the way so you don't have to worry about it anymore. Next thing I want you to do is find the critical numbers, right? So find the critical numbers. Which is when the derivative equals 0 or when the derivative does not exist, right? Those are what the critical numbers are, which means we have to find the derivative, right? So f prime of x is 4x to the 3 minus 12x squared. Nice breezy derivative, right? There are no values of x where this thing does not exist, right? So it exists for all values for all x. Are you guys okay with this upside down a? It's shorthand for all x.
This is the first time I'm hearing of it, so I
know I've been trying to avoid it, but
I have no choice but to be okay with it.
It means for all. Yeah, there. Everyone's accepted it as truth? Great. I know I've been trying to avoid all this kind of math notation, but sometimes it's, in this case, I got lazy. So now you know. Which means that, okay, let's figure out the values of x where this thing equals 0, because we don't have to worry about these critical numbers. So now we're going to focus in on these critical numbers. So I'm going to rewrite this. I'm going to factor this a little bit, right? I can pull out a common 4x squared times x minus 3. So at x equals 0, this thing's going to go to 0, right? And at x equals 3, right, make f prime of x equal to 0. So these are our only critical numbers. This is also where the derivative changes potentially from positive to negative, right? And so critical numbers are x equals 0 and x equals 3. So let's talk about increasing or decreasing. I'll bring in the little blur. That's the wrong handout. Okay. So we know where this derivative equals 0 and it's at the critical numbers. So what we can do is, I like to just do a little number line here. I'll throw down 0 and 3. And then I just pick test points, right? So I imagine x is less than 0, so you can try x is -1. In here, let's try x is 2, and out here we've got, maybe let's try x is 4. Because we know that this is where the derivatives are 0, there's no other, the behavior in each interval is going to be the same, right, until we hit this kind of derivative equals 0 again, right? And so these just represent the whole interval. And if you're able to, you can just think about, okay, well, if x is less than 0, or if x is between 0 and 3, or if x is greater than 3. I personally have a hard time with that. I like to have fake numbers to deal with, but the derivative f prime of x is, let's use the factored version because it's often easier, 4x squared times x minus 3. If I have some value less than 0, so let's try to do it without the test points. If I throw in some value less than 0, it would be negative, right? So a negative squared is always positive, right? Times a negative minus 3 is still going to be negative. So you have a positive times a negative, right? And so this becomes a positive times a negative, oops, not -1, but just a negative, which is negative overall. If you do the same thing in here, so now you're considering values between 0 and 3, right? So f prime of x, and often we'll just talk about the sign, right? Positive 4 is always just going to be positive, so it doesn't do anything, right? So positive times a positive times a negative is going to be the same thing, right? So I'm kind of ignoring that positive 4. You can include it if you want. But now what I'm going to do is I'm just going to go straight from, so I'm not going to write out the specific equation here. I'm just going to imagine x is somewhere between 0 and 3, and just to have a number to work with, I'll think about 2. But 4 times some value between 0 and 3, that's a positive number, squared is still positive. right? So I've got a positive times, and then x is still less than 3, right? So this is going to be a negative value times a negative. So it's still negative overall, a positive times a negative is negative. And then the next region or interval, now I'm imagining some x greater than 3, which means that this is positive, but also the second portion is positive. Right, so I've got positive times a positive, which is a positive overall. Okay. So what that means is that we've got, I'm plowing through this battery.
What it means is we got 5% battery left.
I know, crazy. It took no time flat. Here we go.
It's amazing how math does that.
Let's see here. We are almost done, but I would hate to kind of run out of juice in the home stretch. How can I do this? Uh-oh.
Just use a crayon on your back wall.
Uh-oh. Okay.
And I'm here all week for other very poor ideas.
Okay, I think I got it. I'll just have to be kind of tethered here. Okay. Things are balancing in a weird way. Down to 4%, it's down to the wire. So things got weird. It's like hanging, I don't know if you can see.
We'll just
I guess
not
that
worry
means
about it.
I just got to work faster. So, okay, so what we've established is that we're going to be decreasing up until x equals 0, but then we keep decreasing. That's okay. And then at x equals 3, we change to increasing, right? And so overall, what we have is we have decreasing, and then it switches to increasing. Hey, 6% already. Power surge. Okay, so that's how you find the intervals where it's increasing or decreasing. Great. How about maximums and minimums? And maybe just bring in the first derivative test. So the next thing you're going to do is use the first derivative to find local max or local min, or potentially neither, right? Which we actually have an example of, so that's good. The first derivative test says that, okay, at the critical number, so here, right, suppose that C is a critical number, so we already have our critical numbers 0 and 3, and those are the only ones. And we have a continuous function because we are working with a polynomial. So if the derivative changes to positive to or from positive to negative, then you have a maximum. If it changes from negative to positive, then, and of course we're always moving with increasing values of x. I'm assuming that you're okay with that. Then you have a minimum, right? And so, and then if nothing happened at that critical number, then you have neither, right? So the first derivative test says that at x equals 0 is not a min or a max, and x equals 3 is a local minimum. Important that we say local, right? We're not, excluding other options kind of beyond what we're looking at here, right? So, and that's okay. Local maximum usually means an overall maximum, but we'll just throw on the word local just to be safe. Okay, so we've found that we have a critical number that is not a max or a min, and that's okay. So next thing we want to look at, there we go. Well, things fell, but I'm at 8%, so I guess I'll just work double time. Let's talk about concavity then. Sorry, guys. Should have charged it before. Oh, well. The concavity test now we're going to look at the second derivative. So if the second derivative is positive, then we're concave up. And if the second derivative is negative, then we're concave down, right? Which means that, well, first things first, let's find the second derivative. F double prime of x is the derivative of the first derivative, which puts me at 12x squared minus 24x. Which I am going to factor again, pull out a common 12x. So 12x times x minus 2. Again, kind of similar idea as the critical numbers. We're not going to call them critical numbers, but where it changes, notice that it doesn't include 0 here, right? So where it is 0 are the potential points where it could change from positive to negative. And so here at x equals 0 is one option, and then x equals 2. These are the points where it could change from concave up or down to down or up, if that makes sense, right? So those are the potential points where we could have a shift. Otherwise, they behave the same inside each interval. So again, same idea, right? But now using 0 and 2 instead of 0 and 3, which were my critical numbers, right? I'm going to have 0 and 2 here. And f double prime of x was 12x, 12x times x minus 2. So again, just kind of think about each interval, and I'm going to try it without picking test values now. So if x is less than 0, so if x is negative, I have 12, which is always positive, times a negative, right? And so I have a negative times a negative which means it's concave up, right? So it's positive. So if I go to the next region, if x is between 0 and 2, so now x is positive, right? So a positive times a positive times a negative makes a negative, so concave, I think it's down, right? If it's less than 0, yeah, concave down. And then for x greater than 2, I've got f double prime of x is, so now 12 is positive times something greater than 2, which is still positive. So I've got a positive times a positive, right? 3 minus 2 is positive. Nice. So here, right, from negative infinity to 0, and then from 2 to positive infinity, we're concave up, and then between 0 and 2, you're concave down. Concave up from negative infinity to 0, and then picking right back up at 2 to positive infinity. I'm not including those endpoints because that's where it's equal to 0, right? So I'm not going to include those. And then concave down on the interval from 0 to 2. Oops. And because it changes from positive to negative and then negative to positive, that makes both of these 0 and 2 are inflection points. X equals 0 and x equals 2 are inflection points. And I'm trying to keep it on the same page here. Because it's going from concave up to concave down to concave up. And so that's where it's inflecting. Good. So that's the end. I do want to show the second derivative test, right? But here, this is kind of the complete question. This answers the question. Besides the sketching, we'll do the sketching here, but let's also consider the second derivative test. Right, we can have a look at the second derivative test. Again, it's only going to tell us about these local max and mins, which we already know where they are, so we're good. So, okay, I'm almost done. So we've got a continuous second derivative, fine, it's a polynomial, so we're good. And then we need to consider our critical numbers where the derivative is 0, right, which is at 0 and 3. So, and if the second derivative is positive, then you have a local minimum. If the derivative is 0 and the second derivative is negative, then you have a maximum. So we know our critical numbers are at x equals 0 and x equals 3. So what we're going to do is we're going to find the second derivative because we want it at c, right? So evaluate the second derivative the second derivative, derivative at C, right, which are the critical numbers, or maybe I should say at critical numbers, right, f double prime of C. F double prime at 0, well, we know the second derivative, we had to find it already, is 12x times x minus 2 is 12 times 0 minus 2, putting me at 0, right? 12 times 0 times negative 2 is 0. Not an option, right? Has to be either greater than 0 or less than 0. So here, the second derivative test is inconclusive. So that's why I say, if you don't want to worry about the second derivative test, don't think about it. So here, inconclusive, since we need f double prime at C to be either less than 0 or greater than 0. But if it's equal to 0, then you have to go to the first derivative test, even if you decided to use the second derivative test. So don't worry. But the second derivative at 3 is, I've got it here, 36, which is greater than 0, which, looking here, it means that I have a local minimum at 3. So therefore, x equals 3 is a local minimum. So our sketch here might look something like, let's see here. I know the function equals 0 at x equals 0 and at x equals 3, I have a critical number. And so, and I know that so combining all this stuff, right, I know I'm decreasing into 0, and then I keep decreasing, and then I'm increasing, and we can map our inflection point if we want to. This is also an inflection point, and maybe kind of somewhere around here we have an inflection point, making it really hard for me to trace this, but here we go. Maybe something like that. Okay. So just as a note, or maybe I'll just say notice that the first derivative test is more reliable for finding max and mins, for finding local max and mins than the second derivative test. And I'm going to leave it at that. So pretty fun, just kind of putting stuff together. But if you have any questions, let me know. Otherwise, see you Friday.
Got no questions, though I was sort of distractedly poking around on the course Moodle page.
Yeah.
And was looking at, hey, what was the 1 point x stuff we were dealing with? Oh yeah, exponential functions. Oh, I'm feeling so much better about the course right now because that was just months ago.
Totally, right? Yeah, so I know sometimes it's fun to go way back. You're
It's
like,
like,
oh,
oh,
okay.
yeah. Oh yeah. I remember feeling those were a bit difficult.
Yeah,
Ah.
and if you want a lot of fun, you can go back to 3.1 where we do derivatives of polynomials.
It's like, oh, it's so much easier now. We could just sort of skip right on through it.
Totally. I know, I know. Uh, uh, good. Glad to hear it. I guess I should stop this recording here.